In this video, we're going to discuss our final class of functions, logarithms. You may have heard the term algorithm before, same letters, different arrangement, totally different meaning. While you may have seen exponential functions before, for many of you logarithms will be completely new. And in case you were wondering why we talked about inverse functions when we did, the answer is this, so that we can use the inverse concept to define what a logarithm is. In the most basic sense, a logarithm is the inverse of an exponential. It cancels out an exponential. Canceling an exponential is not the same thing as canceling an exponent. As we're going to see, to cancel out an exponential, you can't just apply a root and be done with it, like you might with x squared or x cubed. It takes slightly more complicated algebra than that. So our goal is to define the algebra that it's going to take to handle canceling out an exponential expression. To relate our new function category to the one we just looked at, exponentials, we need one additional property of exponents, the power of a power. In other words, how do we handle the situation when something with an exponent is raised to another exponent? The answer is that we multiply the exponents together, simplifying everything into one base with one exponent. I want you to keep in mind that any property or identity works both ways. So if we have a power raised to a power, we multiply the powers. But also, depending on what our exponent is, we could decompose it into two exponents that we separate out and then multiply together. So let's define our new type of function, the logarithmic function, but let's start by looking at it from the point of view of an exponential, the type of function we've already seen. So the exponential function is 1 to 1. We can determine this from the graph. It passes the horizontal line test, so it's 1 to 1. If it's 1 to 1, it also must have an inverse. So suppose we were trying to solve for the inverse of a given exponential. So we have y is equal to b to the x power, which is an exponential, and we're trying to find its inverse. So algebraically speaking, the first step to finding an inverse is to invert, to actually switch x and y. So algebraically, we would switch x and y, and we would now have x is equal to b to the y power. So we know the next step to solving for an inverse is to isolate y. But the question now is, how do we solve for y in this situation? So normally, anytime we have something with an exponent, in order to solve for something, we use the related root. So if we're trying to get rid of something squared, we use a square root. If we're trying to get rid of something cubed, we use a cube root. This is a little different though. So whenever we do that, we're trying to solve for the base by canceling the exponent. That's kind of problematic because in this case, the base is constant and the exponent is the variable we're trying to solve for. So if we were to take a root of any type, we're canceling out the exponent. In other words, the thing we're trying to solve for is the thing that's going to go away. So we can't use a root. It doesn't work that way. The answer to this question, how do we solve for y, is algebraically speaking, we can't. So instead of solving for y using algebra we know, we introduce a new type of function that as a whole is going to represent what the inverse of an exponential is. So we have b to the y is equal to x. In other words, we inverted x and y. Conceptually, we solve for y, whatever that means, and y is defined as the logarithm base b of x. So one thing I want you to pay attention to is that letter b. B was the base of the exponential. Now b is written as a subscript for a logarithm, which we call the base of the logarithm. So the logarithm function, base b, represents the exponent to which you have to raise the base, in this case b, to get the desired output, in this case represented by y. X, which is being plugged into the logarithm, is called the argument. So log base b is kind of like f. It functions the same way. So we have f of x. Well, log base b is now taking the place of f. So it's the name of the function we're using. And then whatever's right next to it, in this case we're representing it by the variable x, represents the input that we're plugging into this new function that we're calling a logarithm. So a logarithm represents an exponent. It represents the exponent we'd have to raise an exponential to, so that the exponential would cancel out. So at the moment, this sounds pretty mysterious. So in order to better understand what a logarithm is, it may help to convert from a logarithm to an exponential. So why do we do this? Why does this even make sense? Well, we actually do it all the time without realizing it. So say we have the expression 2 cubed is equal to 8. Well, 2 cubed is equal to 8 is the same thing as saying the cube root of 8 is equal to 2. So we can actually convert between different forms of different expressions all the time in order to understand how a function and how its inverse are related. We're going to do the same thing here. If we have something exponential, we can change the statement into a logarithmic form, and that'll give us a better sense of what the logarithm actually means. So here's some key hints. When we're interpreting or converting an exponential or a logarithm expression from 1 to its inverse, the base of the exponential is the base of the logarithm. So in an exponential, the base is the big number, and then the exponent is the superscript. Whenever we have a logarithm, the base is written as a subscript next to log. So anytime we have a logarithm, the base is going to be the small number. Anytime we have an exponential, the base is going to be a big number. So if we're converting from one form to another, the base of each becomes the base of the other, depending on what we're converting from, what we're converting to. And then x and y always switch places. And this is based on the inverse relationship. So if you remember, one of the things we defined about an inverse fundamentally is that the domain and range switch places. Well, domain is represented as x, range is represented as y. So if we convert from one form to the other, kind of like I just said with something cubed or a cube root, we switch the x and y. In other words, once we determine what the base is, the other two numbers in the problem represent what we're thinking of as x and what we're thinking of as y. So converting from one form to another means we fix our equal sign, and then the other two numbers switch places across the equal sign. So let's try a few examples. So we want to write each equation, each logarithmic equation, in its equivalent exponential form. So remember, the base of the logarithm becomes the base of the exponential, and then the other numbers in the problem switch places across the equal sign. So our first equation is log base 2 of 16 is equal to 4. So just to reiterate, log base 2 is kind of taking the place of f, where we'd normally see f of x. It means the same thing. So log base 2 is essentially the label, the name for this particular function. And 16, even though we're not putting it in parentheses, 16 is considered to be the input of this function, which we formally call the argument. So we're saying log base 2 of 16, whatever that means, it's equal to 4. So the base of this logarithm is a 2. So that means if we convert from the logarithmic form of this equation to its equivalent exponential form, then the base of the logarithm, which is 2, is going to become the base of the exponential. So it's going to be the big number for the exponential. Then we fix our equal sign, and the other two numbers switch places across the equal sign. So log base 2 of 16 is equal to 4 is the same thing as saying 2 to the 4th power is equal to 16. So notice the subscript on the logarithm became the big number for the exponential. It became the base. And then 4, which was on the right-hand side of the equal sign, now moves over to the exponential side. Well, we already have the base, so the only place for it to go is to go to the exponent. So it becomes the exponent, and then everything is equal to 16. So if you remember, we said the logarithm is defined as an exponent. It's the exponent that would cancel out that particular exponential. So in this case, whatever the logarithm was equal to, which was 4, becomes the exponent when we convert to exponential form. Let's try another one. So log base 10 of 1 over 100 is equal to negative 2. So the base of the logarithm is 10. This becomes the base of the equivalent exponential. So when we write it in exponential form, it's going to be an exponential base 10. And then our other two numbers switch places. So in exponential form, the equivalent equation is 10 to the negative 2 is equal to 1 over 100. Let's try one final example. So log base 7 of 1 is equal to 0. The base of the logarithm is 7, so that becomes the base of the exponential. And then our other two numbers switch places. So in exponential form, this is 7 to the 0 power is equal to 1. So the good news is there's a very convenient, very easy way to check your answer. Once you convert from one form to another, make sure that the equation you've written is true. So 2 to the 4th power is 16. That's a true statement. If you try to convert and then you come up with an equation that's not actually true, that means your conversion wasn't actually correct. So the good news is it's always great when you can check your answer. In this case, you can check your answer. The equation you convert to has to make sense. It has to be a true equation. Now let's go the other way. So now we want to write each equation, in this case an exponential equation, in its logarithmic form. The same rules apply, however. So the base of the exponential, in this case, is going to become the base of the logarithm. And then just like before, the other numbers are going to switch places across the equal sign. So our first equation is 3 to the 4th power is equal to 81. We know this is a true statement. We want to convert it to the inverse logarithmic form. So the base of the exponential becomes the base of the logarithm. In an exponential, the base is the big number, so the base is 3. When we write it as a logarithm, the base becomes a subscript, so we'll have a log with a subscript of 3. And then the other two numbers switch places, so 4 moves to the right, and then 81 moves to the left. So our equivalent logarithmic equation is log base 3 of 81 is equal to 4. So again, look at the left-hand side. Let's make sure we understand what we're talking about here. Log base 3 is the name of the function, and then the number next to it, which we write as a full-size number. We write it as a standard size number. This is the input of the logarithm. So if it helps, you can always put parentheses around this number 81. We normally don't do this because it's understood, particularly as you progress in math, that anything right next to anything with a log is considered to be the input of it. But once the input for the logarithm becomes more complicated, we may put parentheses around it just for clarity. So whatever is directly to the right of the log and the subscript is considered the input of the logarithm. It's what we're taking the logarithm of. So again, just to reiterate, overall 3 to the 4 is 81, so log base 3 of 81 is equal to 4. Let's try another one. 10 to the 6th power is equal to 1 million. So our base is 10, which means our logarithmic base is also going to be 10. That's going to be the subscript for the logarithm. And our other two numbers are going to switch places. So in logarithmic form, this equation is log base 10 of 1 million is equal to 6. And then one final example, 1/5 to the negative 1 power is equal to 5. Our base is 1/5 here. It's okay if it's a fractional base. That doesn't change anything. So our base is 1/5, and then our other two numbers switch places. So in logarithmic form, this is log base 1/5 of 5 is equal to -1. So regardless of which direction we're converting, the most important part initially is to identify the base. For an exponential, the base is the big number. For a logarithm, the base is the subscript that's right next to the logarithm. Then we fix our equal sign, and the other two numbers remaining in our problem switch from left to right or from right to left. So this is fine and good when we're given an equation to start with, but what happens if we're just given a logarithm as a single expression and we want to determine what it's equal to? It's not as simple as just moving things around in our equation. We need to know how to actually evaluate a logarithm just on its own without anything that it's directly equal to. So when evaluating a logarithmic expression, we want to write the argument, aka the input, whatever we're taking the logarithm of, as a power of the base. So remember, the base is the little subscript. It's what's written directly to the right of the log. So whatever our base is, we want to write the input in terms of the base. In other words, we're going to take our input, we're going to take our argument, and we're going to write it as that base with some exponent. That's specifically what we're looking for. So we're trying to write our input as an exponential with the same base as that of the logarithm. So let's try a few of these. We want to evaluate each logarithmic expression, determine what it's equal to. So our first one is log base 4 of 16. We want to know, what does this actually mean? What is this equal to? So to help us better understand what this means, how this procedure is going to work to evaluate this, it may help to think of this as a question. Anytime we have something we're trying to simplify or evaluate, we're ultimately answering a question. So if we can rephrase this problem as a question, it may help us better understand what we're trying to do, what we're looking for. So if we were to translate this into a question, the question is 4, in other words, our base, to what power is 16? So the actual question part is to what power? In other words, what is the exponent? So it's saying 4 raised to what exponent is 16. So the answer to our question is going to be the exponent that would make this true. 4 to this exponent gives us 16. So you may be able to figure this out without having to do any additional algebra, but let's demonstrate algebraically how you would get from where we are to where we need to be. So we're trying to evaluate log base 4 of 16. So algebraically, we want to take the argument, the input, in this case 16, and we want to write it as an exponential in terms of our base for our logarithm, which is 4. Well, we know that 16 is going to be 4 to the second power, so we're going to rewrite 16 as 4 squared. And so the answer to our problem, the value of this expression, is whatever the exponent is. Once the base of the logarithm and the base inside the input match up, the exponent is the answer to our problem. So remember, the question was 4 to what power is 16? So the power, the exponent, is the answer to our question, and it's the answer to our problem. So log base 4 of 16 is equal to 2, because it's the exponent we would raise our base to in order to get this value of 16. Let's try a couple more. Same rules. Log base 1/3 of 9. So as a question, this is asking 1/3 to what power is 9? So we're saying if we want to take 1/3 and raise it to an exponent, what exponent do we have to raise it to get an output of 9? This one may not be as easy to immediately figure out as the one for 4 to the second power was 16. So this is where the algebra is really going to help us out. So one thing I want you to remember is 1 over a is equal to a to the negative 1. In other words, our rule for a negative exponent. So a number and its reciprocal are related by an exponent of negative 1. Well, why does this matter? Let's think about it for a minute. So we want to do log base 1/3 of 9. Okay, so we want to write 9 in terms of 1/3, 9 as 1/3 with some exponent. So I don't immediately know how to relate 9 to 1/3, but I do know how to relate 9 to 3, and then I know how to relate 3 to 1/3. So maybe if I can take a couple intermediate steps, if I can relate 9 to 3 and then I can relate 3 to 1/3, then maybe indirectly we can get 9 in terms of 1/3. So let's start by just relating 9 to 3. So 9 is the same thing as 3 squared. So I'm going to rewrite 9 as 3 squared. So now I have log base 1/3 of 3 squared. Okay, so now we still want to get terms of the same base. We still want 3 to be written as 1/3. Well, we know that a number and its reciprocal are related by an exponent of negative 1. So if I want to write 3 in terms of 1/3, 3 is the same thing as 1/3 to the negative 1 power. So I can rewrite that 3 as a 1/3 to the negative 1 power. Now it was a 3 squared, so I still have to take into account that I already had an exponent of 2 there. So the 3 becomes a 1/3 to the negative 1, and then all of that is squared. Well, we remember that power to a power rule because we talked about that at the very beginning. We have something raised from an exponent to another exponent. So in this case, we multiply our two exponents. The combined exponent is the answer to our problem. It's the answer to the question, 1/3 to what power is 9? So whatever our exponent is when we fully simplify, that's the answer to our question and it's the answer to our problem. If we multiply these two exponents together, we get a negative 2. So log base 1/3 of 9 is equal to negative 2 because negative 2 is the power we would raise 1/3 to in order to get 9. Let's try one final example. So log base 2 of 1/8. So as a question, we're saying 2 to what power is 1/8? Now we're in the same situation. It may not be easy to directly relate 2 and 1/8, but maybe we can inadvertently and indirectly relate 2 to some other things, and then maybe we can work our way to 1/8. So we want to write 1/8 as something in terms of 2. So I know I can relate 1/8 to 8, and then I know how to relate 8 to 2. So maybe we can do this in a couple steps, just like we did for the previous example. So let's rewrite 1/8 as 8 to the negative 1. Remember, a reciprocal is related by an exponent of negative 1. So this becomes log base 2 of 8 to the negative 1. 1 over 8 and 8 to the negative 1 power are the same thing. So I'm a little bit closer. I know how to relate 8 and 2. I know that 2 cubed is 8, so I can rewrite that 8 as 2 cubed. So now I have 2 cubed, and I have that pre-existing exponent of negative 1. Now everything is in terms of the same base, so it's a log base 2, and then in parentheses I have a big base of 2 with a couple exponents. I know I need to multiply my exponents. Power to a power, we multiply the exponents. So I multiply my 3 and my negative 1. So the answer to my question, 2 to what power is 1/8? The answer is negative 3. So 2 to the negative 3 power gives me 1/8. So negative 3 is the answer to my question. It's the answer to our problem. So just to summarize, whenever we want to evaluate a logarithm that's standalone, figure out what a logarithm actually means, think of it as a question. The base to what power gives us the argument. So the first example on this page, 1/3 to what power gives us 9. So we want to rewrite our argument, our input, in terms of our base with an exponent. To what power means we're looking for an exponent. An exponent represents our answer. So once we can rewrite our input using our matching base, whatever the exponent is, that represents the solution to our problem. Let's talk about a couple of special logarithms. So we had one special exponential. It was called the natural exponential, and we labeled it with e. So because this number pops up in a lot of different mathematical and scientific situations, we give it a specific label so that whenever I see e and you see e, we know we're talking about the same thing. Well, we have a couple of logarithms that we label specially as well, just because we see them pop up in a lot of situations. The first one's called the common logarithm, and it's a logarithm of base 10. So our number system is base 10. Anything with a base 10 we tend to see a lot in any type of problem. So we're going to relabel a logarithm base 10 so we don't have to write as much. So essentially these relabelings, these shortcuts, are there so we don't have to write as much. Writing log base 10 over and over again is going to get tedious. So in order to eliminate that issue of having to write the same thing over and over again, we're going to simplify our notation. So standard notation would be log base 10 of x. So because we use this logarithm so much, we're actually going to shorten this to just log of x. So we take away the base and then we just write our input. So anytime we see a log with no base number written, it's understood to be a base of 10. So for your purposes while you're learning, you can write in the base of 10, but gradually you need to start phasing out that base of 10. If it's not there, it's understood to be a base 10. So let's evaluate a couple of common logarithms. So let's say log base 100,000. So remember, the easiest way to evaluate a logarithm is if we can write our input as some exponential with a matching base. So we have an understood base 10, so we want to rewrite 100,000 with a base of 10. Well, 100,000 is 10 to the 5th power. You figure that out by determining how many zeros are tacked on at the end of the 1. In this case, there's 5. Once we have everything in terms of the same base, the answer is our exponent, which is 5 in this case. What about log base 1,000th? So 0.001, the 1 is in the thousandths place, so this is 1,000th. Same situation, so we want to rewrite the input in terms of the base. There's an understood base 10, so we want to write it base 10. Well, 0.001 is 10 to the negative 3 power. So in other words, we determine if we were to start the decimal after the 1, how many places to the left would we have to move it to take it to where it actually is. In this case, we'd have to move it 1, 2, 3 times, so our exponent is a negative 3. So our base of our log and our base of our exponential match, they cancel, leaving us with just our exponent. So the answer to this one is negative 3. We have one other special logarithm called the natural logarithm. That word should look familiar. We had a natural exponential function before. It's the same thing. So this is a logarithm base e. E was that special number, roughly 2.72, that we have a button on our calculator for. So in our old notation, we would have log base e of x. We actually shortened this to ln of x. So ln stands for natural logarithm. We just flip the order of the letters. So ln of x means log base e of x. And just like with log base 10, while you're learning, it's okay to convert this to a log base e, but make sure whenever you're entering an answer using a natural logarithm or writing an answer using a natural logarithm, you use this ln notation. So let's evaluate a couple of these. ln of e to the fourth power. So ln is a log base e. In this case, our input has a base of e. So our base of our logarithm and the base of our input match. So our solution is just the exponent, which in this case is 4. What about ln of 1 over e? Well, we have that e in there, so we know we're already halfway there, but we want to write directly in terms of e. In other words, e with an exponent. So 1 over e is going to be the same thing as e to the negative 1 power. Remember, any number and its reciprocal are related by an exponent of negative 1. So we now have a log base e and an exponential with a base of e. So the solution is our exponent, which in this case is a negative 1. Logarithms have some special properties, just like exponents do. First, we have our inverse properties. So logarithms were directly defined as the inverse of exponentials. So each logarithm is the inverse of the exponential with the same base. So because of this relationship between exponentials and logarithms, we have a couple of inverse rules that allow us to simplify expressions where there's both a logarithm and an exponential. So if we're taking log base b of b to the x power, notice our base for our logarithm, our base for an exponential are the same. They essentially cancel each other out and leave us with an x. So log base b applied to an exponential with base b is kind of like the same thing of taking a square root of a square or squaring a square root. Whenever we see the two together, we know they're opposites and they cancel each other out. Well, the same thing is true here. If we have a logarithm of a particular base applied to an exponential with the same base, then they are inverses, they're opposites, they cancel each other out, and what we're left with is going to be the exponent of the exponential. It works the other way as well. So this is an exponential plugged into a logarithm. If instead we have a logarithm plugged into an exponential, so now the exponential base comes first, and the logarithm is part of the exponent. So it's an exponent of log base b. It doesn't matter which order we plug them in. So as long as the bases are the same, there's an exponential base b and a logarithm base b, they still cancel out. So this also leaves us with just an x. So those are our inverse rules. In other words, logarithm, same base as an exponential, they always cancel each other out. We also have some other rules just based on how we defined logarithms. In other words, what a logarithm means. So a couple other special properties. Log base b of 1, regardless of what the base is always equal to 0. So if we were to evaluate log base b of 1, the question we're answering is b to what power is 1? In other words, what's the exponent we raise b to in order to get an output of 1? Well, we know that regardless of what the base is, if we raise it to the 0 power, we get a 1. So if we're going to just use a completely arbitrary base and we want to get an output of 1, the exponent we raise it to is 0. That's what gives us an output of 1. So log base b of 1 is equal to 0. Log base b of 0 is actually undefined. We don't actually have a base for which this is going to be true. So let's think about this as a question. We're saying b to what power is 0? Well, we already encountered this problem with exponentials. We recognize that there is no exponent we can choose such that we can raise our base to that exponent and get an output of 0. On the graphs of our exponentials, this gave us a horizontal asymptote. We got really, really close to y equals 0, but all we're getting is teeny tiny fractions. We're never actually getting something that's identically equal to 0 as an output. So there is no exponent we can raise our base to in order to get an output of 0. So log base 0, or log base b of 0, is undefined. And then finally, log base b of b is equal to 1, regardless of what b is. So as a question, this is saying b to what power is b? Well, regardless of what the base is, if we raise it to the first power, we get the same number out. So log base b of b, the exponent we raise b to in order to get b, is 1. Finally, let's talk about how we would graph logarithmic functions. And we're actually going to use the inverse relationship between exponentials and logarithms to graph. So since a logarithm is the inverse of its respective exponential, in other words, the logarithm and the exponential with the same base specifically, it also defines a function and it can be graphed using this inverse relationship. So we're going to start with the exponential and we're going to use the exponential to graph the logarithm. So suppose we have a generic exponential. F of x is equal to b to the x. So we don't know what the base is. We're keeping it generic. And then also suppose that x comma y is a point on this exponential graph. If we want to graph the related logarithm, that's going to be log base b of x. So it's going to be the logarithm with the same base as the exponential. If xy is on the original graph, then the inverse point is going to be yx. So if you remember when we talked about inverses, one of the key features of inverses was that all the domains and ranges switch places. Well, domain is represented as x, range is represented as y. So to take a point that's on our original graph and find the corresponding point on our inverse graph, all the x's and y's switch places. This is going to be the easiest way to graph a logarithm. If we can generate all the points we need for an exponential, we invert all our coordinates and we have all the points we need for a logarithm. So let's try a couple. So here's our old friend f of x equals 2 to the x. This was the first exponential we graphed, and you'll recall these were the points we got. So we input all of our integers from -2 to 2, and we got outputs of 1/4, 1/2, 1, 2, and 4. So because our base was greater than 1, our outputs increased as our inputs increased. If we plot these points, those should look familiar. Now we want to graph the associated logarithm. So because this is an exponential of base 2, the associated logarithm is a logarithm of base 2. So you might be wondering, why do we even need to do this to graph? Can't we just pick x values and plug them in and graph, just like we did with the exponential? Well, in theory we can. The problem is figuring out what x values to pick. What x values are going to make this easy to evaluate without having to use a calculator? The only x values that are going to be easy to plug into a logarithm are ones that can be written in terms of the logarithm's base. So in other words, plugging in powers of 2. Those are the only things that are going to be easy to plug into a logarithm. So that's not so bad if our base is 2, but what if our base were 1.5? How do we determine what numbers to plug in so that they're going to be directly related to a base of 1/2? That's actually pretty hard to do. So for that reason, because it's easier to determine the points on an exponential, it takes a lot less time just to graph the exponential and then relate it to the logarithm. So we don't have to figure out what x values to pick that would be easy to plug into our logarithm. So the associated points on our logarithmic function based on that inverse relationship are going to have all the same coordinates, but our x's become y's, and then our y's become x's. So it's all the same coordinates, but they switch places. So if we were to graph this exponential and its associated logarithm, this is what we have. So notice they're the same shape, but they're mirror images across that diagonal line y equals x. That was one of the other fundamental aspects of inverses. They're mirror images across the 45-degree diagonal that goes through the origin. We also know that the domains and ranges switch places. So the range of our exponential was 0 to infinity, not including 0. That means the domain for our logarithm is going to be the same thing, 0 to infinity, but not including 0. So this means in terms of what we can plug into a logarithm, we can only plug in positive numbers and evaluate. We can't evaluate a logarithm for anything less than or equal to 0. So it's undefined when we plug in 0. It's undefined when we plug in anything less than 0. We can only evaluate a logarithm for positive numbers. And then also our domain for our exponential function was all real numbers. So the range for our logarithm is going to be all real numbers. And then a special feature we had for our exponential was a horizontal asymptote at the x-axis. In other words, y equals 0, where everything with an x and everything with a y switch places. So if x equals 0, or excuse me, not x equals 0, if y equals 0 is an asymptote for our exponential, then x equals 0 is an asymptote for our logarithm. Well, x equals 0 is a vertical asymptote. So this particular graph, this new logarithmic graph, has a vertical asymptote at the y-axis. So x-axis asymptote for our exponential, y-axis asymptote for our logarithm. Let's try one more. So now we're going to relate a logarithm to the other exponential we graphed, which was 1/2 to the x power. So we had all our coordinates for that one. We plotted those points. Same shape as 2 to the x, but now our points are going in the opposite direction. So this is a decreasing graph instead of an increasing graph. And if we want the points for our associated inverse, in this case a log base 1/2, we flip all our coordinates. So it's all the same coordinates, but our x's become y's and our y's become x's. And if we were to graph each of these, we have a blue graph, which is our exponential. We have our green graph, which is the logarithm. So notice these two graphs intersect. It has to do with the fact that our base was something between 0 and 1. However, they are still both mirror images across that 45-degree diagonal line, so that hasn't changed. Domain and range and asymptotes don't change either. So we always switch our domain and range to get from a function to its inverse. So our domain is 0 to infinity, not including 0. In other words, regardless of the base for the logarithm, the only things we can plug in are positive numbers. This is going to make a big deal when we get to equations. We're going to solve equations with logarithms, and domain is something we're going to have to take into account. Range is also all real numbers. We can get any output we want. And then we still have that vertical asymptote at the y-axis. That is consistent for any logarithmic graph. So let's sum up what we've learned about this last category of functions, our logarithmic functions. Specifically, logarithmic functions are functions of the form f of x equals log base b of x. And then we decided that a logarithm is defined as the inverse of the exponential with the same base. In this case, we're representing it with the letter b. So logarithms are specifically defined so that they're the inverse of the exponential function with the same base. So in other words, a logarithm with a particular base and an exponential with the same base are always going to cancel each other out. And we know that anything in logarithmic form is also convertible to exponential form, which gives us a better picture of what we're actually talking about with a logarithm. The domain for any logarithm is 0 to infinity, not including 0. So the only numbers we can take a logarithm of are going to be positive numbers because the only numbers we can get out from an exponential are going to be positive numbers. So that inverse relationship switches our domain and range. Our range for a logarithm is all real numbers. So although we can only plug in positive numbers, we can get any output from negative infinity to infinity. And then domain, because we have that break at 0, that corresponds to a vertical asymptote on the y-axis. So any logarithm, unless there's some type of transformation involved, is going to be constricted to the right of the y-axis. We're only going to graph to that side. We're never going to touch or cross the y-axis. And there are also two special logarithms. They're ones we see a lot in actual contexts. So nothing really changes except how we label them. So the common logarithm is a logarithm base 10. We use a base 10 number system. So this is a number we use, this is a logarithm we use a lot. So instead of writing log base 10, we drop off the base and just write log. So anytime we see log written without a base, it's understood to be a base of 10. And then we also have the natural logarithm, which is the logarithm with a base of e. We abbreviate this instead of log base e as ln of x.